So in the previous problem, we got up to this. We got a1 b1 bar plus dot 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 plus an bn bar plus c1 b1 bar plus dot 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 plus cn bn bar, and this is nothing but equals to I goes from 1 to n a I bi bar, and this is what summation I goes from 1 to n ci bi bar. Okay, and what is this? This is equal to the inner product between the numbers a1 a2 dot 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 an and b1 b2 dot 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 bn. This is the inner product, the first inner product, and the second one is you take c1 c2 dot 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 cn comma b1 b2 dot 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 bn. Okay, and this is equal to what is a1? It is x. What is b1? It is y. What is c1? It is z. What is b1? It is y. So ultimately what do we get? We have proved that x plus z comma y is equal to xy plus zy. First property is satisfied. First property is satisfied. One thing I'll forget, but it is all of you have to remember this particular fact. I have often seen students writing the thing like this: a1 a2 dot 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 an. Now this doesn't have any meaning. So many dots. Some teachers also do the same kind of mistakes. They put lots of amounts of dots to show that many elements are be present over there. Actually, this is wrong. This doesn't have any meaning. Okay. What we do actually is we write the first two elements.
3 dots.
3 dots. Do you know why 3 dots? Can you say?
No, sir, but our teacher back in 11th, 12th asked the same question, but no one answered it.
What?
Sir, but actually, I always notice that everyone puts the 3 dots, and our teacher also asked why we will put the 3 dots, not 4 or 5. Sir, but we don't have any answer. And
okay. Anybody knows? Anybody from in this class knows this answer? Okay, let's talk. Let's remove the mystery about these 3 dots. It is a1, a2, 2b continued till an. For this 1 dot, for this 2 dot, for this 3 dot. Mystery result. Remember.
Then there should be 4 dots, sir.
No, why?
To be continued till an.
Till is not considered. This word is not considered.
Silent.
It is hidden. It is not actually used. So to be continued means it should be, yes, grammatically it should be to be continued till an, but whenever we are writing an, then it's okay. Everybody understands that till an I'm writing. So it is to be continued, 3 dots. Okay, anyways, next property, cx.
Hello, sir.
Yes.
So please explain once again the second last step, sir.
Which one?
Second last step, sir.
This one.
After summation. No, sir, this step. After summation, sir.
This
Yes.
one, this part. This part.
Yes, sir.
Oh, what was the definition
Yes,
of
sir,
the
yes.
what was the definition of the inner product? You defined the inner product as summation I goes from 1 to n ai bi bar. Now remember, your vector x is from fn and your vector y is from fn. Now what is your vector x? Your vector x is n tuples, and your vector y was also n tuples bn. Now what we are doing over here in this inner product, we are considering the first component of the vector x a1 and multiplying this by complex conjugation of the first component of vector y. We are considering the second component of vector x, multiplying this by this complex conjugation of the second component of vector y, and so on. And we are adding them together. This is the meaning of this operation. Now you see
Yes,
that
sir.
when I am writing ai bi bar, so that means first component of vector x is being chosen, and second component, first component of vector y is being taken complex conjugation. So it is xy. This inner product is xy. This is x, this is y, and we are taking the inner product. This is z and this is y. We are taking the inner product, and that is coming from the definition by which the inner product has been defined over here. Understood?
Yes, sir.
Okay. Now let's talk about this one. Now carefully observe, you'll understood it in a better way. Here we have chosen a scalar. So C is a scalar quantity. Let C belonging to F, and X and Y are vectors. So X, Y belonging to Fn. Okay. So as before, X is this n tuples, Y is this n tuple. So Y, we are writing C into A1, A2 dot 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 AN, and Y is B1, B2 dot 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 Bn. Okay. Now, how do we multiply the vector by a scalar? In Fn, we multiply each of the terms of each of the component of the vector by the scalar quantity. So we write CA1, CA2 dot 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 comma CAN. This is one. This becomes a component as a whole, and we get B1, B2 dot 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 Bn as it is. So we are taking the inner product of this component with that component. By definition, just look at the definition. By this definition, we take the first component of this vector, which is CA1, multiplying this by the complex conjugation of the second complex conjugation of the first component of the second vector. We are taking the second component of vector x, multiplying this by the complex conjugation of the second component of the second vector. So B2 bar. Then we are in this manner, if we go, we write CAN into BN bar. Now, these are numbers, all these are numbers in scalar quantities, and all these products are the scalar products. So scalar products are commutative because we are doing operation inside a field. So we can commute them together in this manner. We can commute them in this manner. And then we can take C common, and we can write it in the following manner. Okay. And what is this? A1, B1 bar, A2, B2 bar, and AN, BN bar. What is this? This is your C into summation. I goes from 1 to N AI BI bar. And that is your inner product as you have defined, which is C into X comma Y. So second property is also satisfied. Second property is also satisfied. Second property is also satisfied. Okay. Can I go to the next page?
Please wait a minute.
Can I?
Yes,
Okay.
sir.
Okay. So number C, property number C. Let X comma Y in be in Fn so that X is A1, A2 dot 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 AN, Y is B1, B2 dot 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 BN. Now I'm going to consider the bar operation over here. Just hold on a second. Just hold on a second. Okay. Oh, sorry for interruption. So now we are going to consider the operation bar over here, and it means I'm putting these vectors in the manner as I put it earlier, and putting a bar over there on the top of it. What is the meaning of this inner product? We all know this is AI BI bar. I goes from 1 to n whole bar. What is this? This is A1 B1 bar plus A2 B2 bar plus dot 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 plus AN BN bar whole bar. What is this? This is A1 bar B1 bar bar A2 bar B2 bar bar dot 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 plus AN bar BN bar bar. Then B1 bar bar is nothing but B1 itself. B2 bar bar is B2 and Bn bar bar is Bn. And we can commute these numbers because these are elements of field. So we can write it as B1 A1 bar, B2 A2 bar plus Bn An bar. And by definition, this is summation I goes from 1 to n Bi Ai bar, which is the inner product between the vector y and x, y comma x. So the third property is also satisfied. Third property is also satisfied. And number D, let x be in Fn. Okay, then x belong is the vector this, and then if I consider the inner product of this x and x, we can simply write it as and that is by definition ai bar summation I goes from 1 to n, which is a1 bar plus a2 bar plus dot 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 plus an bar. And we all know from our we all know from our earlier experience that a1 bar is nothing but a1 square mod a1 square, a2 bar is nothing but mod a2 square, and an bar is nothing but mod an square. Okay, and since if we consider f equal to r over here, then this will be simply a1 square a2 square dot 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 an square. If it is f is equal to c, then this should all be just mod a1 square mod a2 square mod a plus mod an square. Depends upon what particular scalar field you are working with. But here in this particular example, no special scalar field has been chosen. In general, we have considered the vector space Fn over F. And according to the choice of our scalar field, we will manipulate the thing. And this term is always positive, you know. If when it is positive, if a1 not equals to 0, a2 not equals to 0, dot 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 an not equals to 0, that is if x a1 comma a2 comma dot 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 an not equal to 0 vector 0 comma dot 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 0. You have to be very careful about what 0. If you write x is not equal to 0, that doesn't have any meaning. If you write x not equal to 0, it doesn't have any meaning because 0 is a number 0 and x is the vector x. So a vector cannot be equal to a number, or you cannot write x equal to 0 or x not equal to 0. A vector must always be equated to a vector. Vector should not be equated to a vector like this. Both sides on the sign, there must be a vector. So you need to be very careful about this. Be careful about writing what you are writing. Be careful.
Sir, please repeat this part once again.
Which part? Which part?
That comparison part. That comparison part.
I mean, this part, x not equal to 0 part.
Yes, sir.
I'm saying, say, what is x? X is the member of the vector space V, which is Fn. So the shape of x is like this. It is the n tuples a1, a2, dot, 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 an. It is a vector. It is not a scalar. Now, if you write x equal to 0, or if you write x not equal to 0, it means you are writing a1, a2, dot, 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 an is equal to 0. Say, what is 0? 0 is a number. This 0 is the notation for number. But if you write that this is equal to 0, it doesn't have any meaning. It bears nothing. So if you want to equate this vector to some 0 vector, you must write it like this: a1, a2, dot, 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 an should be equal to 0, 0, dot, 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 0, so that all the components can be matched. Corresponding components can be matched from both the sides. Then you can say that, yeah, a1 is 0, a2 is 0, an is 0. So that's why when I am writing that a1 square plus a2 square plus an square, this is positive. That means I mean that they are not individually 0, simultaneously. Suppose you are saying that a1 equal to not equal to 0, a2 not equal to 0, but an is 0. Then it will not bear anything. So simultaneously they are not equal to 0. It is always positive quantity. If it happens, that means these components are not in all 0. That means this x is not 0 vector. And if x is not 0 vector, and if inner product of x with x is positive, that means your last final property is getting satisfied over there. So we see that property 4, this is not part of the problem. This is just an explanation. So property 4 is also satisfied. Property.
Hello, sir. If all 0 except one any value in a1, a2 to a8, then
okay. You are saying that suppose a1 equal to 0, not equal to 0, a2 not equal to 0, dot, 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 but an equal to 0. Or suppose I'm writing it in this manner: a1 not equal to 0, a1 not equal to 0, but every other element is 0. a2 0, a3 0, dot, 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 an is also 0. Suppose this is happening. So that then also a1 square plus a2 square plus dot, 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 plus an square, this is positive always, because this part will vanish, but this part will remain. But what is my property? My property is saying that this must be true. This inner product is positive if x not equal to 0. Now, if you consider it in this manner, it means you are choosing a vector of this form. Okay, you are choosing a vector of this form. So if this vector is okay, this is not a 0 vector, right? This is not a 0 vector. This is not a 0 vector. So yeah, you can do, you are right. Your point is, I got your point. So this is, you can write and or. This is, you can write and or. Then this particular, the doubt that has crept in your mind, that has been eliminated. Now it is all right.
yes, sir.
Now it is all right, because yeah, very good. You have got this particular point. If I write it in this manner, this becomes simply 0 because of my choice of the components. But a1 square still remains. a1 square is positive, and since it is positive, so this is also positive. X is the vector, this one, a1 0 0 0, which is not obviously not equal to 0 0 0. So that will also be okay. So if either all of them together not equal to 0, or any one of these, at least one of them is non-zero, then x is not 0, and therefore inner product of x and x is positive, and therefore property 4 is satisfied. Now it is all right.
Yes, sir. Sir,
Yes.
one more question, sir.
Yes,
In
yes.
property 3, sir,
Hmm.
or second step. In
Second
second
step.
and fourth, no, sir. Third and fourth step, we can interchange due to a scalar, sir.
This
Scalar
one,
fields.
this
We
one,
can
or this one.
first this one, sir. The last one.
This.
A1 B1 to B1 A1.
What is the doubt?
We can change it because of a scalar multiplication.
We can
change
yeah,
it
because
normally in the
because A1 B1 these are elements of the field, and field is commutative with respect to multiplication.
yes, sir.
Field, the
Okay,
members.
sir. I think
You think? You thought?
I think you use any special property for this type.
No,
sir.
no, no, no,
But
no. It is because no. It is because let me write it over here. Commutative with respect to scalar multiplication. That's why.
okay.
Because if f equals to r, if f is a real number set, then simply we know that any two real numbers, x, y is simply as yx. This is the simple thing that that have been used over here. Commutativity. That has nothing to do with any other special property. Okay. So what is our conclusion? Our conclusion is here in this particular case where you raise the question, you raise the doubt, you clarified the doubt at all, it is credit goes to you. You will write it in this manner. Don't write it as and or. You write if at least one of the component is not 0. Let me write it over here. For this particular place, you are going to write this is x greater than 0 if at least one of the components is non-zero, that is x not equal to 0. Write it in this manner. Don't write like and or. This is not the way of writing. So ultimately our conclusion is we saw that under the inner product as defined, in V equal to Fn by x comma y summation I goes from 1 to n ai bi bar. Fn is an inner product space. And the most important part, the inner product, that means this inner product is called standard inner product defined on Fn. It is called standard inner product defined in Fn. Standard. There are two types of important inner products. Okay, one of them which I have elaborately discussed over here. That's called standard inner product. And this important note over here that if x comma y is any inner product on a vector space V, and R is a positive number, we may define another inner product by the rule x, y prime, this is comma, which is equal to r multiplied by x, the inner product of x and y. Okay. You will just, I'm leaving it for you. I have chosen this example from the book itself. Just check. Not now, after the class, you can check at your leisure hour that if xy is any inner product on the vector space V and R is positive number, we may define another inner product by the rule xy prime R into xy. It is also written over here that if R is less than 0 or less than or equal to 0, then the last property will not, last property means D, will not hold. The last property will not hold. Can you check it? This is the inner product now. xy is the inner product defined on the vector space. They have not mentioned fn or anything. They have defined it in this manner. xy is the inner product. Taking R to be the positive number, you have to check whether this inner product, if you define inner product like this, whether xy prime is inner product or not. How can you do this? Okay, let's try it out once. This problem has not been just, they have left it for us. They have not done this particular problem. No problem has been done. Yes, yes.
Sir, this standard inner product function is different for different spaces.
Yeah, definitely. Definitely. After today, I have discussed standard inner product. Tomorrow, I am going to discuss another inner product, which is called Frobenius inner product. Frobenius inner product.
This standard product is only for Fn.
Yes.
Okay.
This standard inner product is only for Fn. There are some other various inner product, various different inner products are there. And the most important two of them, all of these, all inner products are this standard inner product and that Frobenius inner product. Frobenius inner product is actually used in quantum mechanics, not standard inner product. You will get to see gradually. Okay, so now let's concentrate on this particular note. Yeah, Arif Ali.
Sir, you said that the inner product of two vectors gives us a scalar, that is a number, right?
Yes.
So the inner product of, for example, the inner product of x and y gives us k. So the inner product of y and x will also give us the same result.
No such thing has been written in the property. In the property, I have not said that inner products are commutative. I said this rather. I said this will happen, but I never wrote in the property that this will happen. This is missing. No such property is there. Got my point?
Yes, sir.
Yeah, so it is not always true. And also remember that inner product, the standard inner product is usually called, you know this name, standard inner product is usually called dot product. But there is a catch actually. It is not that easy as you are thinking. What is dot product? Suppose we have a vector A, we have a vector B. And in the school, we have learned that the dot product between the two vectors is actually modulus of these vectors and multiplied by cosine function, that is of theta, where theta is the angle between the two vectors. This is A and this is B. We know from our school days. And from there, we can also write it as A dot B by mod of A vector and mod of B vector. We all know this. But in the book, if you have the book in front of you, you see that in page number 330, it is written that standard inner product is usually called dot product. Any clever student can ask me right now, that, okay, sir, we have understood the inner product, that is standard inner product is there. You have defined so many properties, but you are saying that standard inner product is usually called a dot product. In dot product, we know that there is an angle, a cosine function of some angle is there. So where is the angle in your inner product? It must reflect the angle. So where is this angle? Isn't it the question that coming to your mind?
Yes, sir.
Yes.
Yes, sir.
Yes, exactly. That question must come to your mind. But remember, this is the byproduct of something which have been cooked and have been produced in front of you. But this is not the way the things were actually developed in mathematics. The cooked product, the processed food, we are being eaten in school, but the way it was developed that time, when inner product was actually developed, no idea of angle was introduced in it. To introduce the idea of angle, we need another item which is called norm. You will learn it. You will learn this norm is there in your syllabus. This norm is very important term, which if not introduced, you cannot introduce the concept of angle. Angle in what is theta? Theta is actually the cosine function, cos inverse of this quantity. Cos inverse of this quantity, mod of A, mod of B. Okay, but you see, carefully observe that here in this case, I know what is this. It is inner product. We can calculate the inner product between the two numbers. But what is modulus? Modulus has not been defined. Modulus of the vector has not been defined in the definition which I have provided you in the inner product space. So this modulus will be defined by the quant term which is called norm, which is the generalized version of the mod, which denotes the length. We'll try to identify the angle in terms of inner product between the two vectors and their norms. Okay, so this idea is this development, the way it was developed is quite difficult. It was not that easy. And therefore, even if I'm saying the standard inner product is usually called a dot product, but not right now, it is not called dot product until unless you introduce the concept of norm. They have cleverly written in page number 330 that is dot product, but they have not mentioned where the angle is. But if you keep on reading later chapters, you will find that somewhere they have defined the norm, and gradually they have introduced particular thing into the picture. The development is very difficult actually. So we used to write from you wish to walk from left to right usually in generally, but now we are actually moving from right to left. Okay, so that is the thing. Now, since the time is almost running out, probably I'll not be able to complete the discussion of this note, but you try this out at home and try to identify that this happens. XY prime is inner product. Consider R greater than 0. So what you need to check, for example, you need to check, say for example, let's try only one. We have 5 minutes. So it is given that XY is inner product. So it satisfies all the properties. Is inner product. It satisfies all the properties defined in our previous discussion. Now, what is my inner product here under consideration? It is XY prime. Now, XY prime is defined in the following manner: R into XY. Okay. Now, how can you show that the linearity property? Take here, they have not chosen B equal to Fn. So you cannot say that X is A1, A2, An and Y is B1, B2, Bn. Not like this. They have considered this to be any V. So be very careful about this. It's any V. Take X, Y, and Z from V, defined over a field F. Then X plus Z comma Y, this should be equal to, if I consider X plus Z to be another variable, well, let us denote this variable by T. So let X plus Z is T, then we can write it as simply Ty. Now this Ty is what? Okay, don't have to write it as ty. Sorry, we don't have to write it as ty. Not required. Since this is inner product, okay, I am want to consider this x plus zy prime, not x plus zy only, xy plus zy prime. That is our objective. Now, okay, let us consider x plus z to be t. If it is t, then we are actually getting ty prime. What is ty prime? By definition, xy prime is r into xy. So ty prime will be r into ty. Now replace t by x plus z. So we get x plus z comma y. Now you know that xy is inner product. So therefore you can apply the property, the first property on this inner product. You cannot apply directly on prime, but you can apply it on inner product, this inner product. So we can write it as x comma y plus z comma y, since xy is inner product. Now r is positive, and you will multiply these particular terms individually. Okay, and this is equal to xy prime by definition, and this is equal to zy prime by definition, which shows this prime is also linear in its first component, and therefore xy prime satisfies property A. Understood? How to proceed? Students, I'm asking you.
Yes, sir.
Yeah.
Yes,
Be very careful about what you are using, what you are writing. Probably you were thinking how to show it. The solution has not been shown in the book, but you have to be very careful. Remember, I know that most of the students, if I would have left it for you, most of you have thought that probably x is this like component like thing and y is component like thing, but it is not. It is B is not Fn here. B is any vector space, and R is positive number. Only information given is xy is inner product. Now another inner product has been defined, so you have to consider the information regarding this inner product into this and to develop all the properties for this new inner product, which is denoted by prime, where R is positive. Now the next important part that you need to check, all the properties B, C, D you check, and what it is written over here, if R is less than or equal to 0, then the last property, if R is negative or 0, then xy prime will not become an inner product, because the last property D will not hold. This much they have said. So you need to check this one. You need to check this one, that if R is less than 0, what happens to the property D? Why it is not getting, it is not being satisfied for negative R and 0 R. Okay, so you
Hello?
need to check the, yes. Tell me quickly, time is running out.
because it become negative, sir. R is a negative value
Exactly.
and R square is positive.
Exactly, but you have to write it properly. The way of writing should be clear. The presentation is actually very important over here. Each step actually counts and actually demands logic. How you reach from one step to another, that is very important. So tomorrow I have a class from 2:30. I have been given a class with CSE section by at 2:30 p.m. tomorrow. So we are going to meet tomorrow and let's continue our discussion on inner products with further problems. Okay?
Okay, sir.
Yeah, I'm stopping here right now. Bye.
Thank you, sir.
Yes.
Thank you, sir.
Thank you, sir.
Welcome.
Yes, sir.